first part of 6.4. 6.4b on electrolytic cells will follow. So for this lesson, we're going to describe how to assemble an electrochemical cell. This is the basis for how a battery is actually made. So if you put several electrochemical cells together, you can actually generate a battery. We're going to look at defining the anode and the cathode of our electrochemical cell and describing how electrons travel between the anode and cathode. We'll look at the role of the salt bridge, describe differences in standard electrochemical cells with non-metal or non-metal ion half cells, and then we'll look at predicting some standard cell potentials from those. So first off, you can see a picture on the top right-hand side of the page here. This is a standard electrochemical cell. You can see that there's kind of two reactions going on all at once. One of the halves of the reaction is taking place in the left-hand beaker there with the zinc sulfate solution and zinc anode. And on the other side, we've got the copper cathode and the copper sulfate solution. We've got the other half reaction taking place there. Connecting the two is a salt bridge and a wire in which electrons flow through. So we're going to be looking at the parts of that electrochemical cell in a bit. Electrochemical cells are also called voltaic cells or galvanic cells, and they're portable sources of energy. In these cells, what we're doing is we're converting chemical energy to electrical energy, and we're doing that by a spontaneous redox reaction. So it works by separating the oxidation and reduction reaction and then connecting them via that external circuit. So if we want to set up an electrochemical cell, this is kind of a demo that I often do in the classroom, we start with two beakers. What we're going to do in those beakers is we're going to put in a solution with ions the same as a bar of metal. So if I have zinc metal, I'm going to use zinc ions. If I have copper metals, I'm going to use copper ions, etc. In this particular example, I'm going to use magnesium metal and magnesium ions. So I might use a magnesium sulfate solution, for example, and copper metal and copper ions from perhaps a copper 2 sulfate solution. Next, I'm going to connect the two metals. So I'm going to connect the magnesium and the copper with a wire, and I'm going to connect that with a voltmeter so I can see how much current is actually generated. Finally, to complete the circuit, I'm going to add a salt bridge. And the salt bridge can have a number of different salts in it. The rule of that salt bridge is to connect the circuit and make sure that cations and anions can flow between the two beakers and kind of level out. In this particular situation, I'm going to put ammonium nitrate, and I'm choosing ammonium nitrate because ammonium and nitrate are both spectator ions and won't participate in the reaction, nor are they going to precipitate out of the reaction. So when we get all of that said and done, you can see that we've got four things that we can kind of pick from that may start our reaction. We've got magnesium, magnesium ions, copper, and copper 2 ions. So what we're going to do is we're going to look for the strongest oxidizing agent and the strongest reducing agent, because those are the two in which the reaction is going to take. So if you look at your standard reduction table, the strongest reducing agent, the one that's farthest down on the right-hand side, is magnesium. The strongest oxidizing agent, the one that is on the left-hand side, highest up, is the copper 2+. So in the magnesium beaker, we're going to be having magnesium donating 2 electrons and becoming magnesium 2+. That's the oxidation part of our reaction. In the other beaker, we're going to have the copper 2+ combining with the electrons and becoming copper, the solid. And that's the reduction part of the reaction. How these electrons are moving is through the wire that connects the two metals. So you can see the electrons move from that oxidation reaction to the reduction reaction, and the ions are coming from that solid magnesium. As the magnesium donates the electrons, it dissolves into the solution, becoming the Mg2+, and so it makes more Mg2+ ions. With the copper, as the electrons accumulate on the surface of that copper, the Cu2+ ions go pick up the electrons and become solid copper and deposit themselves on that copper rod. So the magnesium rod actually gets lighter, the copper rod gets heavier. The last part is that salt bridge, and the ions in the salt bridge are going to move from one side to the other. We're going to have NO3 nitrate ions moving towards the oxidation side, and we're going to call that the anode because we've got anions moving towards the anode, and the cations, the NH4 plus, are going to be moving towards the reduction side. That's the cathode, so cations to the cathode. Now with these reactions, that oxidation reaction is going to be generating positive 2.37 volts. So we're reversing the sign because we're showing that this reaction is kind of going in reverse. The reduction part of the reaction is going to be generating 0.34 volts. When we add those together, we can figure out the potential of the cell. So the E naught of the cell is 2.37 plus 0.34, overall 2.71 volts. And if we connect several of these electrochemical cells in series, we can add up that voltage and get something like a 9-volt battery. So we can put several of these reactions taking place all at once and generate larger voltages from there. So again, anode is where the oxidation reaction takes place. I always remember it because anode starts with a vowel. Oxidation is a vowel. Another way of looking at it is anode, or oxidation has an A in it, anode. Same with cathode is where the reduction takes place. Cathode starts with C, reduction has a C in it. So some things to note from this electrochemical cell is that electrons always flow through the wire from the strongest reducing agent to the strongest oxidizing agent. We had a couple of new definitions in this particular part of the chapter. So we had anode, this is where the oxidation half reaction takes place, and cathode, where the reduction half reaction takes place. Anode is where the anions move towards, cathode is where the cations move towards. Also, good things to note is the direction of electron flow. So electrons always flow from anode to cathode, so from A to C, that's alphabetical. And electrochemical cell is just made up of solid metal in solution that has the ions of the same metal. One other thing here is that at the anode, as the solid magnesium donates those electrons, that magnesium becomes part of the solution, so the anode is losing mass. It loses electrons and it loses mass. Not really related. At the cathode, as those electrons are gained, they react with the copper ions and are plated out as copper metal, so the cathode gains mass. Finally, the role of the salt bridge. A salt bridge, or you can sometimes have a porous barrier, those allow ion migration to take place between the cells, and that's what completes the circuit. If you try and run a reaction like this without a salt bridge, it's not going to generate any voltage because the circuit won't be complete. So within that salt bridge, the anions always migrate towards the anode. That balances out the charges from those electrons being lost. And the cations migrate towards the cathode, where we are gaining electrons, and that balances the charges as well. Finally, looking at non-metal ion half cells, we can do this with a non-metal electrode as well. What you do with a non-metal electrode is immerse it in a solution that has ions of the same non-metal. So if I'm using chlorine gas, for example, here, I'll immerse that in a solution that has chloride ions. And if we're using a liquid or a gas, we're going to use some sort of setup with an inverted test tube that's filled with that liquid or gas, and then using an inert metal like platinum or carbon to use as the site of electron transfer. So that's a way of doing it as well. So some electrochemical cells look a little bit different because they don't actually have the physical metal that's being hooked up. So here's a quick check that I'd like you to try. So we've got an electrochemical cell taking place on the right-hand side, and see if you can answer the following 4 questions. Pause the video and then I'll go through the solutions. This particular cell, the first thing that we're going to look at is what is my oxidizing agent and what is my reducing agent. So we're going to look down to the bottom right-hand side of the chart to try and figure out what the strongest reducing agent is. Strongest oxidizing agent, top left-hand side of the chart, and you'll see that it's silver ions and chromium metal. With this, we can then go and label which parts are the anode and the cathode. We're always going to be having electrons flowing from the anode to the cathode. So the chromium metal is losing electrons, so that's the anode. And the silver there is going to be accepting those electrons, that's the cathode. So there's the electrode that's the anode is the chromium. The direction in which electrons flow through the wire is from anode to cathode, so chromium to silver. Now cations flow through the salt bridge towards the cathode, so they're going towards the Ag+, the beaker with the silver ions in it. And the electrode that gains in mass is going to be the silver. And the reason for that is as electrons gather on that silver bar, we're going to have silver ions from the solution come join onto there to pick up the electron, and they're actually going to deposit themselves on that particular electrode. If we want to calculate how much voltage this will produce as well, we can take a look. We've got 0.80 coming from the silver reaction. We're going to switch the sign on the chromium reaction, so we have 0.74, and as we add them together, we get a total voltage of 1.54 volts. You'll notice that if we look at the overall reaction, we have 3 silvers ions plus chromium yield 3 silver plus chromium ion. Even though we've balanced that reaction and had to multiply the silver by 3, it does not affect the voltage. So predicting standard cell potentials, we've done a couple of these already, predicting the voltage that will result from one of these reactions. We've got our redox potential. So this is the tendency of a redox reaction to occur. It's measured in volts, which is a difference in electric potential, and it measures the difference in potential energy between the 2 points in a circuit. When we're determining this, we're going to write out each half reaction with their oxidation or reduction potential. A reminder that if the reaction is going backwards from your standard reduction table, we have to reverse the sign. It's kind of like looking at a KB, except it's a much easier calculation. Just flip it from a negative to a positive or from a positive to a negative. Okay, and then add the two together. You will also note that if you're adding a negative, it's like subtracting. So here's one more example. Determine the voltage of a standard cell consisting of a nickel 2+ half cell, and iodine I- half cell as well. So we're going to write down the 2 half reactions. You'll notice that for the nickel reaction, we're flipping the sign because it's going backwards. And we can predict the voltage of the cell. E0 is going to be 0.80 volts. When we balance everything, everything just gets added together. Here are 3 more practice problems for you to try. So pause the video again, see if you can do these three particular reactions, and then come back for the answers. So in the first reaction here, we write our 2 half reactions. We've got an E0 of 1.09. With the nickel reaction, because it's going backwards, we're going to flip the sign. We balance that full reaction, balancing those electrons, and we find that the E0 of the cell is 1.35 volts. With the second reaction here, again, we're going to flip the sign for the aluminum reaction, and we take 0.34 plus 1.66, gives us an overall E0 of that cell of 2.00 volts. And with this one, we had to do a little bit of balancing. So we put a 3 with the coppers, 2 with the aluminums. That way we've got 6 electrons being donated and 6 being received. It does not affect our E0. Last one here, we've got gold gaining 3 electrons. We've got iodine losing electrons. When we balance this one, we're going to have to put a 2 and a 3. It's not going to affect our voltage. And we get an overall E0 of 0.96 volts. So I hope this was useful for you, and good luck with some practice problems, and we'll see you in the next video on electrolytic cells.